To remove the low energy X-ray photons, what will pass through? The high energy ones, because the low energy ones experienced absorption and attenuation, so they did not pass through. Consequently, a part of the intensity and a part of the number of X-ray photons were removed from my spectrum, which is this part right in front of me. That's why the intensity dropped significantly in this initial part with the low energy. The reason for this is that it removed this part and did not allow it to pass through. Now, if I increase the kilovolts, for example, I currently have it set up like this, and I made an adjustment on my machine for the low kV, and then I raised my kV from 80 to 120. Based on the curve you see here, or the spectrum you see here, can you tell me what happened? What do you see that has changed significantly, such as the intensity or the number of photons? When I ask you what happened, you will ask me what happened to the intensity, what happened to the minimum energy, what happened to the maximum energy, okay? The intensity, the minimum energy, the maximum energy, and the average energy as well. So now I am talking about 4 things. Do you see if the minimum energy has changed? Or how is it? It's time. I'm talking about 4 things. Is the minimum energy affected? It hasn't changed, right? What about the maximum energy? Has it changed or is it the same? Okay, has the intensity number changed or is it still the same? Great. Has the value of the characteristic changed? It's still fixed because, as I said, this is a characteristic of the target material itself. I haven't done anything. My whole idea is that I gave you an increase, nothing more. So, has the average energy increased or is it still the same? I mean, I said that the average energy or effective energy is considered to be 1/3 to 1/2 of the maximum energy. So it takes the maximum energy and divides it by 3 and by 2 in that range. That is the average energy. The average is the average of the energies of the X-ray photons that are already produced from the X-ray tube. We can say, to make it easier for ourselves in the calculation, half of the maximum energy. So if I operate at 80, what would half be? If I am working at 120 kilo electron volts, what is the half? 60. Great. So what happened to the average energy? It increased. What happened to the maximum energy? It increased. What happened to the intensity? It increased. What happened to the minimum energy? Nothing happened. So the increase in kilovolts led to an increase in the acceleration, which resulted in an increase in the interactions that occur between them and the target. This increased the X-ray photon energy and the X-ray photon numbers, thus increasing the intensity and the average energy. Now, when I say I have fixed my kilovolt and increased the current from 200 milliamps to 300 milliamps of the high current, what happened in the spectrum together? The low energy and maximum energy are almost the same. There is no difference. There was no change in the minimum energy and there was no change in the maximum energy. So was there a change in the characteristic? There was a change in the average energy, or was there not? There wasn't, because it doesn't depend on it. Okay, what happened is that there was a change in the intensity of radiation. All right, the peak was here, and suddenly the peak became high. Here. All right, go ahead. Here, I used a filter or did not use a filter. I increased the thickness of the filter I used to eliminate the air that will appear in the X-ray photos. If I didn't have any filtration, this blue line represents the shape of the curve in the normal case. If I increase the filtration, what will happen? First, the maximum air remains the same. So why did the minimum energy change? It changed because when there was no filter, it was very good. Therefore, the minimum energy changes with filtration. The characteristic X-ray does not change. Did the average energy change or not? It changed. Why did it change? Why did it increase? Let's explain it to make it clearer. If I have from 1 to 100 kilo electron volts photons, okay, their average is 50, right? That's the average energy. Now, if I remove the first 30 from them through filtration, what are the energies I have left? For example, if you stay from 30 to 100, the readings will range from 30 to 100, and it won't be 50. It will be increased to around 65. So what happened? The readings increased because you applied filtration. When we talk later about the artifacts, the city artifact, you might hear about something called beam hardening artifacts, or you might find that in a slice or in, for example, nails. There are areas where black appeared or black streaks are present, right? Doesn't this happen in your X-ray photos? For example, this is related to beam hardening. Beam hardening is the same concept we are discussing, where the X-ray beam itself is an insulator on the patient before encountering a high-density material. What happens is that it removes all the soft energies, all the weak energies, which increases the average energy and thus increases the penetration power of the X-ray passing through the slice. Consequently, when it reaches the detector does not understand what to do. It starts observing the X-ray photons that have reached it and begins to perform normalization. It notices that this area is coming from a high intensity, which means it is coming from low-density materials. On the other hand, if an area has low intensity, it indicates that it is a high-density material. So, it starts to say, well, I am receiving high intensity or high energy here because beam hardening has occurred and the average energy that reached me has increased. And it begins to translate this into black color. It appears dark because it will be considered a low-density material, so it will lean more towards the plaque. That's why you see in the image the plaque strikes that are present due to the presence of the strips and screws and such. The idea here is based on what I'm saying about the concept of filtration or beam hardening. Is that clear? Yes, that's right, doctor. So, the inherent filtration is what? Do you have any ideas to clarify? So, the filtration types, are they clear? You have two types of filtration. One is from the envelope itself, which is the inherent filtration, and the other is if you place a filter on the portal X-ray tube itself. So, I have two types of filtration. If I increase this filtration, it will affect things. For example, in mammography, you use a specific type of filter that is different from the regular X-ray tube and different from the CT. Each application has its own specific filter, so your X-ray spectrum will differ. However, the inherent filtration is related to the house or the envelope of the X-ray tube itself. Is everything clear so far? Or are there any issues? I also want to ask you, can the 120 kilovolt be used now? People are saying that the 120 kilovolt is correct, right? No one uses the lower cases, I swear. Most of them are pediatric cases. A 120. So do you think if we used a kilovolt of 100 or 80 with a moderate sized patient or a thin patient, would the image be acceptable or not? If we are working with pediatric patients, how many kilovolts can we use? Maybe 80 kilovolts would be acceptable because the thickness is less. Okay. Well, there's something. I don't want to skip while I'm talking now about the spectrum and the kV. We can talk about this part later, but I want to discuss the relationship of kilovolt, specifically in contrast cases. You may know that when you increase the kilovolt, the image will appear with better quality, like an enhanced image. This concept is particularly relevant in computed tomography or CT scans, but this is not always true. So when I have my KV, whether I use low energy KV or high energy KV, what does that mean? It means that the quantity or number of photons I have with low energy KV will be less than the number of photons and the energy of the photons present in high energy KV. All right? So the transmitted X-ray photons that will pass from the patient in the case of low energy KV will be fewer than the transmitted X-ray photons that will pass from the patients in the case of high energy KV, right or wrong? Right, exactly. Great. Now, when the number of photons that will pass from the patients and reach the detector or the image receptor is low, what does that mean? It means there will be noise. What does the word noise mean? So I have noise. What does the word noise imply? It means that your image receptor or your film or your picture consists of pixels. For example, you have mobiles. For instance, this mobile is 10 megapixels and another mobile is 20 megapixels. The more the number of pixels increases, the higher the resolution of your camera, right? Okay, these pixels in any image, like in a CT scan, contain information. If I have a value for each pixel, and if all the pixels in my image have the same value for the information, meaning the same number of photons reaching each pixel, for example, if the first pixel in the first row receives 10 photons, and every pixel receives 10 photons, then in this case, is there variation between the number of photons present in each pixel compared to the others, or is everything constant? Each pixel in my image contains 10 photons, 10 signals. Is that clear? No, there is no variation, no excitement, no change. Now, if I reduce the number of photons that will reach my image receptor, will the probability of variation in the pixels increase or decrease?
Variation increases when variation increases, which means there are pixels that do not contain the same number of X-ray photons that reach them. For example, some pixels may have 10, some 5, some 3, and some 7. This variation occurs because the number of X-ray photons reaching the receptor is not sufficient to provide a good image. This phenomenon is referred to as noise, and it particularly occurs with low KV settings, especially if I have a fat patient. The fat patient will absorb the radiation incident on them, resulting in very few transmitted photons, which leads to the appearance of black dots in my image, due to those pixels not receiving enough information to provide a clear image. Therefore, the smaller your patient is, the more you can reduce the KV comfortably. However, for a fat patient, I work at 120 kV. The area being imaged, such as the skull, has high bone density, so a higher number of X-ray photons and higher penetration power are needed, which increases the TV. In an area like the pelvis, where there is pelvic bone, higher penetration power is also required, which increases the TV. In a pediatric case, for a child, I only need 1 second to adjust the power of the lab. Hello, doctor? Sorry, I was just saying that the laptop was shutting down. Okay, so I need to choose the appropriate value for the examination. Here, for example, you can see the images. This is a CT image, right? And here, for instance, is the aorta. There is a contrast agent here, and here is also a contrast agent, but in a different quality. Which one do you expect to have higher quality, and which one has lower quality? You will discover that the image with higher quality is the one above, while the lower quality image is the one below. So why? The image above is a smooth image. If you look at any part of the background here, you'll find that the image is a bit more sharp than here, so the noise here is higher than here. This image is smoother, but the contrast of the aorta here compared to the background is less than the contrast of the aorta here for the background. So why? Even though I'm using high kV, it should be good, because the contrast agent absorbed most of the X-ray photons. The same contrast agent is present in both images, meaning the same patient. So why is it that when I used a lower value here, the image came out with high contrast, and I could see the aorta clearly against the background, while here, the image is not clear? And I have the same idea I mentioned about calibration, power, and voltage. Calibration equals more production on the film. Subscribe to the channel.
This means that when the penetration is lower, it will show less indication, while with low kV, the penetration is lower, which will also result in less indication. Right, doctor? Because when I used high kV, the high kV has a high penetration power, so X-ray photons will pass through the dye, and the X-ray photons will pass through the dye, the fat, and the air. The concept of the city image itself relies on having contrast between the objects or the organs. This contrast occurs due to the differences in the various densities. So, how do I maximize this difference? By using low kV, because when I use low kV, the penetration power will allow my high density object to absorb radiation distinctly compared to the background. The contrast agent appears very bright compared to the background. Why? Because it is a high density material, thus the change in X-ray photons is not significant, allowing it to be stopped and absorbed, which clarifies the difference between it and the background. Conversely, in the image above, the change in X-ray photons was able to pass through the materials, resulting in a smaller difference between it and the background. Recently, there are many applications discussing the use of low kV. If you are talking about 80 kilovolts or 100 kilovolts with the theme patient, especially in angiography cases, it is very effective and produces images with very good contrast, even if the amount of contrast you are using is minimal. The concentration of the contrast agent is low, which means it is very effective in enhancing the quality of the image produced. This is particularly important in medical imaging. So, when exactly should I consider using high kV techniques, especially in cases where I have patients with higher body mass index, like this? In fatty patients, and in imaging the pelvis region, for example, I need to increase the kV in my settings to obtain a good image and eliminate the artifacts that are present in the image. These are some of the issues with kV levels when dealing with a fatty patient or an obese patient. However, the standard kV today is 80 or 100 kV, which is more than enough for thin patients or moderate size patients as well. But for a fatty patient, we are talking about 120 kV with a maximum of 140 kV. This means that for a very obese patient, we are looking at 120 kV at most, up to 140 kV, indicating that the patient is extremely fat. There is also something that improves contrast resolution. What does that mean? It means that there are two objects or two organs with not much difference between their densities, like the focal lesion that is always present between the liver. The difference in Hounsfield unit is not significant. If you use high kV, with high penetration power, the difference in contrast decreases, making it difficult to see clearly. However, if you reduce the kV in such cases, it provides you with high contrast resolution, allowing you to see the object or lesion that has a difference in Hounsfield unit compared to the surrounding organs. I don't know. If you all are with me like this, or if you feel that the world is closed off, or is the information becoming more established? I don't know. I am just trying to connect the information to something related to the other launch, and I am only afraid that you might be closed off to me because I am discussing topics or introducing things related to the launch. So if you are distracted and want to proceed in a specific and systematic way, that's fine. If this method is better and helps us understand better, then we can continue like this. The method is good, Doctor. Alhamdulillah. You will also find many publications discussing the topic of KV, even in cases of coronary angiography. There is a study here that compares the use of 100 kV and 120 kV, and the difference is very clear. The contrast of the coronary arteries at 100 kV is better than at 120 kilovolts. So, we understand the role that kV plays. There is a very important point that can also be explained here, which is what made the kV relevant to me, or this part that allows us to engage in the interaction. However, it is not a problem if the dye or my contrast media absorbs. Is low energy better than high energy? Is the kV penetration of X-ray the only factor, or is there something else? What about radiation concentration? It seems to create radiation close to the energy of X-ray photons. Yes, you are getting closer, that's right. But let's clarify it more. The X-ray that is incident on the patient causes different types of reactions. It creates interactions, right? There is a type. I have the X-ray that is directed at the patient. The first X-ray that comes out of the X-ray tube, as we were explaining to you, is it polyenergetic or monoenergetic? We said it is polyenergetic, right? So if I set the adjustment to 120 kV, in this case, the average energy, right? So if I set it to kilovolt. In this case, it will be approximately 60 kV, as we mentioned, that the average is 1/2 to 1/3 of the maximum energy. Now, if I give the patient 80 kV, then my average will be 40 kV. Great. The X-ray is incident on the patient, falling on the patient, which contains bone, soft tissue, muscle, water, and fat, all different materials with varying densities. The interaction that occurs between the X-ray photon and the different materials present depends on the density of the material and the energy of the X-ray photon. If this energy is low, meaning we are talking about low energy from the X-ray photon, it results in what is called a photoelectric interaction, where the X-ray photon interacts with the electron. The electron that is present in the electronic shell around the nucleus gives all its energy, and this electron is emitted. In this case, I call it a photoelectron. This photoelectron undergoes a process called photoelectric absorption, meaning it absorbs energy completely. So, when does this happen? It occurs with low energy kV of X-ray, which increases the likelihood of this photoelectric interaction with high-density materials like pigments, bones, and similar substances, enhancing the occurrence of this interaction. The second interaction involves the X-ray photon. It does not interact with the outermost layer of the electron and causes its emission in any significant way. Part of its process involves the electron moving, and it also undergoes scattering.